colors, like in fireworks.
Yeah, those brilliant greens or reds.
Or the glow from a neon sign, that very particular color. Even starlight, right? It looks white, but it's actually carrying information.
That's exactly it. That light, it's not just happening randomly. It comes from atoms releasing energy, but it's incredibly precise. The specific colors, the wavelengths, it's like a code.
A coded message from the atom itself.
Pretty much, yeah. It tells us something really fundamental about what kind of atom it is.
Okay, so that's what we're diving into today, using the material you shared.
Yeah.
We want to unpack that link, the atom's internal structure, the electrons.
Orbitals, yeah.
How that connects to the light, the photons it spits out, and how that light basically acts as its fingerprint, its identity as an element.
It's honestly one of the coolest things in physics, isn't it?
It really is.
The idea that we can look at light, whether it's from like a lab sample or a star billions of light years away, and we can figure out what it's made of just from the light. It all comes back to this atomic code.
Okay, let's dig in. To really get this, we need to rewind a little bit to how we used to picture the atom. Early 20th century, there was that model. Electrons orbiting like planets.
Right, the classical model. It seemed logical, little things orbiting a central thing.
Felt intuitive.
But it had a massive flaw. According to the physics back then, an electron doing that should constantly radiate energy, lose speed, and just spiral right into the nucleus.
Which would mean, poof, atoms collapse.
Instantly, yeah. And clearly, atoms are stable. The world exists. So that model, it just wasn't right. Something fundamental was missing.
And the answer came from quantum mechanics, which has turned everything upside down.
Completely. Quantum mechanics says forget those neat little orbits. Electrons don't follow fixed paths.
Okay, so what do?
They exist in these three-dimensional zones around the nucleus. We call them electron orbitals.
Orbitals, not orbits.
Exactly. Think of them less like tracks and more like probability clouds. Regions where the electron is likely to be found.
And here's the really key bit from quantum mechanics, right? These orbitals, they correspond to very specific energy levels. They're quantized.
Yes, exactly. Quantized. The source material uses a great analogy. Think of a staircase.
Okay.
An electron can be on step 1 or step 2 or step 5, but it can't hover between steps.
No in-between energies allowed.
None. The energy levels are discrete, fixed values. Like the height of each step is fixed. That's quantization.
So the electron is stuck on these specific energy steps. And the height, the energy of each step, that depends on the atom itself.
Precisely. It's mainly determined by the number of protons in the nucleus, that positive charge.
So the nucleus's charge sets up the specific pattern of these energy steps for each atom.
That's the crucial differentiator. Different number of protons, different set of steps.
Okay, so we've got electrons in these specific quantized energy levels. How does that lead to light being created? Where do photons come in?
Right. It's a two-part process. First comes excitation. An electron absorbs some energy from outside.
Like a little kick.
Yeah, a kick of energy. And if it gets just the right amount, it makes an instantaneous jump, a quantum leap from its current energy level to a higher, empty one.
Jumps up the staircase.
Jumps up the staircase.
Right.
But, and this is critical, that it has to absorb exactly the right amount of energy. The energy difference between the step it's on and the higher step it's jumping to.
It has to be precise.
Totally precise.
And what kind of energy kicks work? Where does it come from?
Oh, various sources. Heat, maybe, if you heat something up.
Okay.
Or collisions, atoms bumping into each other. Or electrical energy, like running a current through a gas in a neon sign.
Right, like the neon sign example.
Yeah, anything that can deliver that specific energy packet needed for that specific jump.
Got it. So absorbs the exact right energy, jumps up to a higher level.
Yeah.
But you said that's unstable.
That excited state, yeah, it's unstable. The electron has too much energy. It wants to get back down to a more stable, lower energy level.
Yeah. So it falls back down the staircase.
It does, spontaneously. And when it falls from that higher step to a lower one, it has to get rid of the extra energy, the energy difference between the two steps.
And that's the light, that released energy.
That's the light. It's released as a single packet of light energy, a photon.
Okay, absorbs energy, jumps up, falls down, spits out a photon. But the light isn't random, you said. It's specific. This is where it all connects, right?
This is the absolute key. The energy of that photon that gets emitted, it is exactly equal to the energy difference between the high level the electron fell from and the low level it fell to.
So the size of the energy drop determines the energy of the photon.
Perfectly. The source material had that example say an electron drops from a level at -2 electron volts down to 1 at -5 electron volts.
Okay.
The difference is 3 electron volts. The photon that comes out must have exactly 3 eV of energy. Not 2.9, not 3.1, exactly 3.
That direct link energy drop equals photon energy. That's the foundation.
It's everything for spectroscopy, yeah.
Hmm.
That nugget connects the atom structure to the light we see.
And we know, physics tells us, a photon's energy relates directly to its frequency and its wavelength.
It's Planck's equation, yep.
And wavelength is what our eyes see as color, for visible light anyway.
Correct. So, because those energy levels in the atom are discrete fixed steps, remember?
Right, this staircase.
An electron can only make jumps between those specific levels, which means the atom can only emit photons with those specific energy differences.
Which means specific wavelengths. Specific colors.
Exactly. It can't just emit a continuous rainbow. It's restricted to a very specific set of colors dictated by its allowed energy level drops.
Okay, this has to be where the atomic fingerprint idea comes in.
Yeah.
How does this make each element unique?
It goes back to the nucleus again, the number of protons. That defines the element, right? Hydrogen has 1, helium has 2, sodium has 11.
Their atomic number, yeah.
And that unique number of protons creates a unique electric field, which dictates the exact energies of all the electron orbitals for that specific element.
Ah, so hydrogen's staircase is totally different from helium's staircase.
Completely different. And sodium, with 11 protons, has its own, much more complicated, but still totally unique set of energy levels.
Okay, so unique element means unique energy levels, which means the possible jumps, the possible energy drops the electrons can make, are also unique for each element.
You got it. That's the heart of it.
And since the photon energy matches the energy drop,
each element emits its own unique set of photons with its own characteristic energies and wavelengths when its electrons get excited and fall back down.
so if you take the light from, say, excited hydrogen gas and spread it out with a prism or a spectrometer, you don't get a rainbow.
Nope. You get what's called an atomic emission spectrum. It looks like a series of sharp, bright lines of specific colors on a dark background.
Just lines.
Just lines. Each line corresponds to a specific electron transition, a specific energy drop, a specific wavelength emitted by that element.
And the pattern of those lines.
Yeah.
That's the fingerprint.
That is the unmistakable fingerprint. The source material nails this. Hydrogen has its pattern of lines. Helium has a completely different pattern. Iron, a very complex but unique pattern.
No two are the same.
Never. That specific set of lines, those wavelengths, is the element's unique ID card, written in light.
That is genuinely amazing. So how do scientists actually use this, put the fingerprint to work?
Well, this whole principle is the foundation of atomic emission spectroscopy. It's a hugely powerful technique.
How does it work, basically?
You excite the atoms in a sample, maybe heat it in a flame, zap it with electricity in a plasma.
Those electrons jumping up.
Exactly. Then you collect the light they give off as they fall back down, pass that light through a spectrometer to separate the wavelengths.
And you see the lines.
You see the pattern of lines, and you compare that pattern to known patterns for all the elements.
So you can tell exactly what elements are in the sample just by reading the light signature.
Precisely. It lets us analyze what's in all sorts of things. Metal alloys, soil samples, water purity, even things like checking the authenticity of materials.
Wow. And you mentioned stars earlier.
Yeah, that's maybe the most mind-blowing application. We can analyze the light coming from stars and galaxies that are incredibly far away. Pass that light through a spectrometer, identify the line patterns, and figure out the chemical composition of objects across the universe, all without leaving Earth.
Just by decoding the light. It's incredible that something so fundamental, the energy levels inside an atom, creates such a specific readable signature in the light it emits.
It really connects the quantum world to the cosmos, doesn't it? The atom's deepest structure dictates the light, and that light carries its identity everywhere.
So here's something for you, our listener, to think about, building on what we've discussed from the sources.
Yeah.
Next time you see a distinct color of light, maybe it's that orange glow from a sodium street lamp, or the colors in a shop sign, or even just thinking about starlight. Remember, you're not just seeing light.
You're reading a message.
You're essentially reading a coded message, an atomic fingerprint, sent directly from the atoms themselves, telling you exactly what they are. All thanks to quantum mechanics and these unique light signatures.